Science 10, what's going on? It's Mr. Walton here. We're doing another video. I don't know if it feels the same way to you because we're on our second day now. It's day 2 of kind of learning online, and this is kind of weird. It's really odd not having people in front of me. Usually I can gauge people's emotions and how they're feeling by seeing them. So I just want to let you know I've got absolutely no feedback as to whether or not y'all are getting it, if you know what I mean. Are you getting this? So let me know in the Google Doc if you have any questions. Show up in the Google class meeting during 10:45 to 11:15 during office hours if you have any questions. Otherwise, I don't know. I kind of just have to assume that you guys are getting it. So anyways, whatever. That's okay. So today, we're working on classifying types of chemical reactions. And so there's 5 types of chemical reactions. And we have to be able to recognize these chemical reactions from a mile away. What I mean by that is you should be able to spot the type of chemical reaction just by looking at it, okay? Now, there are 5 types of chemical reactions we must be familiar with. Predicting reactions will be much easier if you commit to recognizing these reactions, and they're all right here. But also, this information is on page 10 of the data booklet. Now, this is fairly straightforward, but we're going to go through this, and it's going to take a few minutes for us to just be able to define all of this stuff. But here's our 5 types of reactions: formation, decomposition, single, double replacement, and hydrocarbon combustion. So let's take a look at some analogies, and then let's take a look at some real-life examples of what's going on here. So the first thing we're going to do is we're going to look at a formation reaction. Now, keep in mind, it's this little table here is telling us that a formation reaction, whenever you form something, then that means you're taking 2 or more things and smushing them together and making something more complicated. In general, a formation reaction is an element plus another element to make a compound. So the analogy that we like to use for this is getting married, where you've got, one element and it's going to combine with another element and it's going to make, holy guacamole, it's going to make a compound. And so that compound is, a combination of 2 elements. Here we've got element number 1, we've got element number 2, and we're going to make a compound that is those 2 elements put together. Now, a real life example of what's going on there is when you have aluminum reacting with oxygen. If I was to react oxygen in the air with, react aluminum in the air with oxygen, so we take aluminum solid and react it with oxygen from the air, gas, and we're going to get aluminum oxide or aluminium oxide. Now, aluminium oxide is an ionic compound, so Al3 plus and O2 minus. When I put those together, I get Al2O3 solid. Perfect. So this is an unbalanced reaction, but right now that's fine. We're fine with unbalanced reactions just for the moment. So hopefully you can see how this would be. This would be a formation reaction. We've got an element plus another element, right? Aluminum all by itself is an element. Oxygen all by itself is an element, and it's going to make a compound. And this is a compound because it's 2 or more elements put together as one substance. So hopefully it makes sense. A formation reaction should be fairly straightforward. 2 things combining together to make something more complicated, that's a formation reaction. Now let's go back. We can see the next one is decomposition. So let's go up here and let's see what a decomposition is. So that's a compound turning into two elements. It's something complicated, and it's being broken apart and turned into two simpler substances, specifically elements. So this, well, I don't know, hopefully you can see that this seems like it's the exact opposite of a formation reaction. So unfortunately, the analogy that kind of makes sense to a lot of people is getting divorced. So we'll take a compound that's made up of more than one element, right? We've got two different elements here, and they're going to get divorced, or they're going to break up, and we're going to get two different elements from this. So this is something really complicated, and it's turning into two things that are less complicated. So a compound turning into its two elements. Okay, all right, we get it, Mr. Walton, we get it. So that's a lot like the reaction of water. When I take water and I run electricity through it, I can split up water and turn it into its two elements. I can decompose water. Well, if water decomposed, what would it turn into? If the H and the O's split up, what would they turn into? Well, they'd turn into hydrogen gas and oxygen gas. So here we have, just like we had before, we have a compound turning into an element plus another element. Perfect. So hopefully you can see how decomposition and formation reactions, they're the exact same as each other, they're just opposites of each other. Okay, so let's move on. You probably saw a sneak peek of the next thing that we were going to do. We're going to skip all the way to hydrocarbon combustion. Now, hydrocarbon combustion is when you burn something. That's basically what we're doing. We're taking a hydrocarbon, and a hydrocarbon is basically anything with C something, H something, whatever. It's any combination of C's and H's. That's why we call it a hydrocarbon. Hopefully that makes sense. It's a hydrocarbon. Sorry, that was a little bit patronizing, but hopefully you get it. So this hydrocarbon is going to react with oxygen, and all the time, if it's complete combustion, we'll talk more about this at Chem 30, but if this is a hydrocarbon combustion reaction, you will always make carbon dioxide and water, and we should be pretty specific, it's water vapor when we burn something. So carbon dioxide and water vapor every single time, and you'll notice it, you'll be able to see this from a mile away because it's a hydrocarbon plus oxygen. Hydrocarbons are very obvious to see. Okay, all right, no problem. The reason why we say getting hot and steamy, getting hot and steamy is because these hydrocarbon combustion reactions, I mean, what do you think happens when we burn something? It releases heat. So that's why it's hot. First of all, it's getting hot because it releases heat to its environment. And then it's getting steamy because it's making H2O gas. That's water vapor. Water vapor is steamy, right? I don't know. Well, whatever. That's okay. Hopefully that makes sense. So let's take one of the simplest hydrocarbons that we possibly can, and let's talk about methane. Hopefully, you remember what methane is. Maybe you don't. That's okay. Whatever. Methane is CH4. And when I react methane with oxygen in the air, I'll show you a video of this in a couple days, but when I take methane and react it with oxygen in the air, I will always get carbon dioxide and water vapor. Always, always, always. So that's a reaction. I'm not going to draw much here for hydrocarbon combustion for the analogy, but that's okay. Now let's move on. Let's move on to single replacement reactions. Single replacement reactions are a compound plus an element, and this element here it kicks out one of the elements from this compound. Typically, we're talking about the compound is typically an ionic compound. And remember, the ionic compound is a positive ion and a negative ion, right? It's a cation and an anion bonded together. This element, let's say this element was a metal, okay? Metals can turn into positive ions. If it's an element, it's got no charge, it's an atom. But if this was a metal, it would kick out the thing that's most likely to be a metal, the positive ion. If this was a non-metal, it would kick out the thing that's most likely to be a non-metal. That's what a single replacement reaction does. So you want to focus on what the element is. And the analogy that we use, you'll have to forgive me, the analogy that we use is a third wheel steals yo date. So imagine you're on a date with somebody and you're having a fantastic time, right? Here, let's draw this out. It's just, trust me, it'll be okay. So we're gonna draw this out. Here's you, and here's yo date, okay? And so then some third wheel comes by and kicks you out. Now, if this thing was a metal, right, you've got positive and negative ions inside this compound. The metal can become a positive ion. If it's an element all by itself, it's not a positive ion yet. But what this metal does is it can kick out the positive ion in that ionic compound, and what you'll get is that the metal has now turned into a positive ion. It's with yo date, and you are left without a date, and everybody's sad. Well, you're sad because somebody stole your date, but whatever, that's okay. So hopefully that kind of makes sense. That negative ion is still negative, nothing happened to it, but the metal turned into a positive ion, and now you're neutral. You're a neutral metal, just like that element was earlier. So an example of this is like when you take, and I'll show you an example of this a little bit later, sorry, I just lost my train of thought. When you take copper metal and you react it with silver chloride, some sort of a silver chloride solution. So we've got copper with no charge. Now the silver is acting as a positive ion, the chloride is a negative ion. Now this copper, it can be a positive charge. I'm not saying it is right now because it's neutral. It's got no charge. It's an element, okay? But it can become a positive charge. So what it's going to do is it's going to kick out the silver, and what we're going to get is we're going to get copper chloride and silver metal. And so hopefully you can see how the silver and the copper switched spots because they're both metals, right? They're both positive ions or can be positive ions. Hopefully that makes sense. And you can see this from a mile away because it's an element plus a compound gives you a compound plus an element, or an element plus a compound again. Okay, so that's single replacement reactions. Now let's talk about a double replacement reaction. Double replacement reaction is the exact same thing as single replacement, except instead of a compound plus an element, it's two compounds reacting together. And so what we have is we have a double date partner swap. And so I'm going to draw the exact same thing I had here. We've got two people on a date, and they come across, this is kind of weird, please don't judge me, they come across another two people on a date, And these two people are like, hey, we can both be positive ions, right? This is a positive and a negative, and a positive and a negative. And so the two positives say, well, you know, it doesn't really matter if I'm with the negative or you're with the negative. So they end up swapping places. And so what you end up getting is you end up getting this positive is with this negative now, and this positive is with this negative now. And that's not what they had before, right? So now the red positive is with the purple, whereas the red was with the blue. Whatever, okay, you get it, you get it. So we should be able to see this from a mile away, hopefully, because a double replacement reaction is a compound plus a compound, and it's giving a new compound plus a new compound. So either the positive switch or the negative switch. That's kind of the way you want to think about it. And an example of this is like, okay, let's try it out. Oops, sorry. So we've got sodium chloride reacting with silver nitrate, and they react together. And so, okay, let's think about this. The sodium is the positive ion and the silver is the positive ion. They're both metals, right? Okay. And so what's going to happen, sorry, you keep moving the page on you, is they're going to swap places. So we're going to get, as our products, we're going to get silver chloride plus sodium nitrate. Perfect. So hopefully, I don't know, it's fairly clear to me, but you take a look at it and you try it out on some of the practice examples that I'm giving, and you see if you can classify these reactions. We're going to keep working on classifying these reactions. We're going to keep working over the next week on this. This is not going away, so please try and put in the work right now, and it's going to be a little bit easier as we go along. Let me know if you have any questions. Fill out the Google document if you want, put a question in the Google Doc, or you can sign on to the Google Meet and you can ask me directly yourself anytime between 10:45 tomorrow and 11:15. Thank you very much. See you later.